Mine? That's alright. Saw part of Figaro last night, that was good.
It was so good.
Oh, yeah.
That was really good stage to it, actually.
Yeah, the set was cool.
That last set.
The last time they did it.
Oh, really? Yeah.
We're not gonna talk about that.
It was good.
Yeah, but, hey, get your homework. Where's Emery?
Only a check?
Okay, guys, I only put checks on that one because everybody got it all right, okay?
Except for Jenny.
And then,
Oh.
Jenny didn't even get it checked because I forgot to.
Because she's the worst.
It was like, so those pluses and minuses don't really mean anything, it just meant that how much effort you did in the last one, okay? Sweet, today is the day you've all been waiting for, we're gonna talk about formants.
Yay.
I didn't know that
Yay.
this was the day I've been waiting for.
Well, everybody keeps asking me about formants, so.
Is it gonna be a great day?
It might be a great day.
Oh.
Alright, first we're gonna review though. So, have you all looked at the Google Drive and seen your health assignment?
Yes.
Or your health presentations?
Yes.
So you go to Google Drive, go to health presentations. There's a thing that says vocal health presentations.
Do we each have assigned topics?
Yes. You read through it. See how it says your name?
Oh, see it.
Right there. Those are the ones you present on with your group.
Yes.
There's another page. Okay, so those aren't until the end of the semester, right? I just want to make sure you all know that that is happening. Okay. It is a group project.
Too much party.
Do I need to clarify any more of this?
No, sir.
No.
Scroll down like half a page.
You're assigned to vocal disorders.
First one.
We were down.
Does anybody else want to see this one?
I like that one. Too much party can count.
Too much
Yeah.
party can cause cancer.
Yeah, it doesn't say can cause.
And party and
Oh.
There's also STDs in that
Oh,
one.
that's kind of funny.
Too much partying. Okay, anyway, whatever.
boo-boos.
Everybody got that?
Yes, thank you.
Wait, I got the dates when the presentations. Those might move because I'm asking a chiropractor to come talk to us about like bone stuff too, but I'm not sure. They haven't replied to my email, so we'll find out. Okay, good. So let's review resonance before we start talking about formants. Okay, because everything that we've talked about in the last two classes basically equals formants. So if you don't understand that, formants is really difficult to get. Okay. Good. So we talked about three elements of a way that sound is produced. Can you guys tell me what they are?
Power source.
Power source is what?
Vibrator.
Vibrator then resonant, right? Good. So you have to have those three things in order to make sound. Good. The voice articulates with what?
With the resonator as well as vibrator.
Right, resonator. Okay. Which is really important because no other instrument's going to do that. Okay. That's why that's important. Good. So then we had the sound.
Wait. Don't you mean a resonator and a vibrator?
Yeah.
Oh,
But
okay.
the resonator is the important part.
Oh.
Because it's like the trumpet changing shape when
Got
you
it.
play it. Do you know what I mean?
Yes.
So it's very like physicsally. Okay, good. Good. So then we had a definition of sound. There are two parts to it. That about the resonance, definition of resonance. There's the intensification and enrichment of sound, and then the supplementary vibration caused by supplementary vibration. So what does it mean when we talk about resonance as an intensification and enrichment of sound?
Resonator amplifies the other tones.
Right, amplifies, right? Which means makes louder. Yeah, good. And then what about supplementary vibration?
Coloring the sound that we get.
It's not by the vibrator source. You get supplementary resonance with it, right? Everybody clear on that?
Yes.
Sweet, good. All right, then there's three types of resonance, yeah?
Yeah.
What were those? Arlene, don't tell me, you're just reading from the PowerPoint. Okay, whichever one is fine. What?
Forced.
Forced?
Slash supplemental.
Supplemental, yeah.
and free.
And free. Good, so what is forced resonance?
Supplemental.
The
It has to
thing
be
that actually
touching
hits the thing.
physically.
Yes, it's the vibration of what is physically moving, right? That makes a sound. Then the supplementary,
Is what results from the forced resonance that I was mentioning.
right. So if it's like a string vibrating on a violin, it's the body of the violin vibrating, right? Good. And then free resonance is what? What we hear, right? There's also, so like a room, it has free resonance to it too, right? So a concert hall, etc. Okay, good.
Do also the cavities in your head have free resonance? Or is that forced resonance because it technically goes through bone and cartilage?
When you feel it, it's forced resonance, okay? If it contributes to changing the overtones of the sound, so like say, when you put your soft palate down and it goes through your nose, that's a chamber of free resonance because it changes the sound.
But forced resonance is not changed.
But forced resonance like is the sound,
Oh, great.
right? It's the vibration of whatever. So the forced resonance is like our vocal folds vibrating, right? And then us feeling like our chest going, that's supplementary resonance. And then free resonance is what makes it sound like E or A or Ah,
Cool.
okay? I know it's a little complicated, but we all gotta have these specific definitions for everything. Good, and so then I had 6 chambers of free resonance, yeah? So we have to know all 6 of those, okay? Right? Laryngopharynx, oropharynx, oral cavity, nasopharynx, and nasal cavities, piriform sinus. And you should be able to identify them on a picture, okay? So that's all I'm testing on.
Oh, we have to see a picture.
There's a picture in my PowerPoint.
Great.
There's a picture in PowerPoint.
That's something you said we might have to do on an exam?
Yep.
Okay.
Okay, good. And then we talked about phase and destructive interference, yeah? So phase is the relationships of 2 different waves to each other, right? And then destructive interference is,
When they cancel each other out.
yeah, good. And then so if we had constructive interference, what's that?
That's when they're the same and then they
Yeah, and they
amplify.
amplify each other. Good, yep, awesome. And then we have the half-length resonators, which resonate all the harmonics, which I'll explain this a little bit better. I realized that I didn't get that much in class, but the formats will help explain that, okay? So we had the equation for that, which was what?
R equals C over 2L.
2L,
or
right?
4.
Because it's 2 of the wavelength. Yep, good. And that has all the harmonics in it, right? And then for the quarter length resonator, it has only the odd harmonics. Did I just say the same thing twice? Half length resonator has all the harmonics in it. Quarter length resonator has only the odd numbered ones.
Interesting.
Okay, and so this is, I thought about this a lot. When you have a half length resonator, it'll have all the harmonics because you can divide 2 by 1. So like the length, you can divide by 1, and you can divide it by 2, you can divide it by 3, you can divide it by 4, and you get all the equations. Whereas if we have like a quarter length where it's 1/4, we can only have 1/4, 3/4, because if we had 2/4, it'd just be a half length resonator, right? That's why we don't get the even harmonics, okay? And so I'll show you, there's this graphic. So it's a little hard to read from where you guys are, but this is the quarter length, right? So that's a quarter length of a sound wave, right? So it's from the top of the compression to the null point right there, right? That's a quarter of the length. And so then this one has to be a 3/4. 1, 2, 3, in order to get to the end. Yeah? So that's why we only get the odd harmonics. That doesn't mean that the even harmonics aren't produced, they're just not resonated. Okay? So they're not amplified by the resonator. Make sense? Okay, good. I know that's a little like far-fetched sometimes, so. Cool. Alright, that's what I want to review with all that, okay? Ooh. Oh, I didn't even pass my lead. Formats. So basically what we're going to do for the next week, we're going to talk about formats today. Next Tuesday, we're going to read the chapter on analysis, and then I'm going to talk about analysis. And then on Thursday is when we have Kurt Stallman's going to come in, and we're going to use some of the spectrographs and power spectrums to like look at our voices and what they do with everything. Okay? So that's what's coming up. And then after that, then we'll have the quiz the next Tuesday, and then we'll start talking about the anatomy stuff, right? Cool, awesome. Alright, so there's a source filter theory, which basically means that there's a source and a filter to every sound, right? The source is produced by the vibration of our vocal folds and the air in our lungs, so that's how we get that but sound, whatever. It's just this part of our vocal tract. So, wake up. Right. So we just get the vibration of it, right? And then the filter is this part, which is also the resonator, right? Okay. Resonators and articulators of the vocal tract. So we can, it's filtered by if we did like a t or a k or something like that. That is also part of the filter in this theory. Okay? Yeah. So it's a lot like a speaker setup with a CD player or something. You get a CD player and then an amplifier. Or yeah, there we go. Thanks. So we have a CD player, plays the CD, right? Sound source. Then we get the amplifier that we plug it into that amplifies the sound, and then it goes into the speakers to be made into sound. Yeah? Cool. Moving the resonances of the vocal tract creates attenuation to different frequencies like an equalizer. Do y'all know what an equalizer is?
No.
Okay, it's a part of a stereo equipment that basically has like bands of frequencies that you can amplify or de-amplify. Like you have it, so if you turn the bass up in your car, that's an equalizer.
Oh.
Okay. If you turn the mid-range down or the treble up, that's an equalizer. They have ones that are like huge, you know, so there's like a whole bunch of different ones you can do. But so basically that's what we're doing with any kind of resonance, we're changing what the frequencies are amplified and de-amplified, okay? Good, so now we have the source. This is still talking about the source filter theory. The vocal folds vibrate generally in an even spectral slope, they call it, okay? The spectral slope is the fall off of amplitude and the harmonics of the sound. So each one of these little lines is a harmonic, right? Let's say that that's the fundamental pitch, and then we get the first harmonic, or second, whichever you want to call it, right? So the octave above it, and then we get the octave in the fifth, et cetera, okay? So notice that these, so it's a graph, this is relative amplitude in decibels, right? And this is frequency in kilohertz. So like this one, when we get to 1,000, that's already a high C. Okay, a high C, like a soprano high C is 1,000 hertz. So we really don't get that much of a fall off in volume as soon when we get to 1,000. Like 2,000 is kind of where we hear our singers form it and things like that, which we'll talk about today. But just so you know, so this is like, it's a huge scale. To go up to 5,000, you know, that's like really high. Okay? So generally even, when we sing, technically you want about 6 decibels of fall off in your harmonics, which is the top one, okay? If you were singing breathy, it's 12. And if 18, that's like really bad, you get a lot of fall off in your spectral slope, you don't even make it up to your singer's formant area in 2,000 kilohertz. And so you really won't be heard over an orchestra or anything like that, okay? Does everybody understand how this works?
No.
Okay, so this is the source, this is at your voice. There's a fall off in how loud the harmonics are, depending on how pressed or breathy you phone it. Okay, and the voice has a really even one. So like say, if you whistle, or if you play like a cymbal, or something, like a cymbal that has like a pitch, you know, so like a crotales or something like that, they have like really strong first harmonics and then they fall off right away. Because it has to do with the source. So if it's like a circle thing and it's vibrating, it just vibrates that octave in a fifth really strong, okay? But so in our voice, it's really even.
Okay.
But you just have to take that for,
Meaning we vibrate all the harmonics fairly evenly.
yes,
Got it.
at the source.
At the source.
So it changes when you add the resonator to it, okay?
Got it.
So this is just, because it's just going, you know, how that sounds like it kind of has pitch, but it sounds very like, a diffuse, like it's very sh-y too in its way, because it has so many harmonics to it, okay? Does that make sense?
Yes.
And so if you have a pressed phonation, sometimes you get like -3 decibels per octave, and some people argue that that's why a lot of like really dramatic singers like to sing pressed all the time, is because it actually makes your voice louder. You think it does. It makes your voice louder.
Pressed as in like.
Like, ah! Yeah.
Ah.
Okay, because it makes your voice louder. There's this whole thing we can measure, like this comes from how long your vocal folds are closed, is how loud these harmonics get. So the more they're closed, the stronger the harmonics are. We're not gonna look at it, but we'll talk about it in an
The
analysis, okay?
longer they're closed,
If they're stronger. So if they're open more, it sounds breathier, and that's why the slope goes up about it, right? It's different, right? It has more harmonics in it.
You mean the longer they're closed in each oscillation?
Yep, got it, yep. They call it a closed quotient. We'll talk about it when we look at the analysis stuff. But you can measure it by putting the EGG meter on the sides of your larynx. And so it puts electrical current through your voice, and it can, when it's open, the current doesn't go through, and when it's closed, it goes through, so you can tell when they're open and closed.
That's right.
what is it?
It's called an EGG meter, we'll talk about it.
Thank you.
Okay, so that was the source. Everybody got the source?
Yeah.
Sweet, filter, quarter wave resonator in our voices, that's what it is. Moving the resonator in favor of different frequencies changes the harmonics that are amplified, okay? So if we have the spectral slope, it's just a slope that goes down like this, and now all of a sudden we're gonna amplify some of those, like with our equalizer, right? So we're gonna turn up some of the harmonics, some of them will get turned down, etc., depending upon what kind of shape our vocal tract is in. Make sense? Cool, alright. We want the pitches and the overtones to be sung, to be properly amplified where we want them. This is how we understand what our vowels are, if we stick our overtones in the right amplifications, okay? I'm flipping out through. Okay, good. So a quarter wave resonator actually boosts amplitude sometimes by like 6 decibels per octave, so we see that it goes up across the spectrum. And we can measure these things, I'll show you too, okay? Our hearing is especially sensitive around like 2000 hertz, which is right where the singer's foreman is. And so that's why we're like really attuned to hear that over an orchestra, because it has to do, so if we have a resonator that's a voice, and we sing, so we talked about there's like a little spot here that makes it so that frequency vibrates a lot. We have that same distance in our ears, so when we hear it, it amplifies it even more. Okay, cool, huh? Good, so this is what it looks like. This is the granddaddy of the source filter theory. So we have the spectral slope, which is this, right? It comes from our glottis, vocal source. Got that? And it goes like this, it falls off a little bit continuous here. And then it goes, we get the vocal tract gain, they call it here, which is this. So say, right here, our voice is gonna amplify those frequencies. Okay, it's going to de-amplify these ones, and it's going to amplify these ones again. Does that make sense? You all look so blank-faced. So basically what it means is that it amplifies, it goes up here, so you add that. And then we end up getting the output sound spectrum of this. Okay?
Can we start at the beginning of this slide again?
Yeah, and something that would be particularly helpful to someone who's never talked about any of these things before, I don't know if there's anyone
It's
in this
okay,
class.
that's what I'm teaching you for.
But
There's 5
instead
of
of
you.
like just saying, see how this goes up, like talking about like what that actually means realistically. Like I know how to read a graph, but like I don't really understand.
Like how do
What
we
any of
measure
these things are
this
trying to show.
in like what I hear in a singer? Like how do we measure this? Like what is a singer, like an example of a voice that has a really, really high or low quality of, you know, one of those?
Okay, did you read the chapter we talked about?
No.
Okay. So they say, these, depending upon where this is how we hear vowels.
What is this? Yeah, that's my
The amplitude of the harmonics,
great. That's very helpful.
right? Okay, so if we all, I know I didn't tell you to bring your books. So this is really why I wanted you to read this chapter. So we get, depending upon what the voice shape is, we get this, is what it sounds like. So this is the amplification and how loud all the harmonics are, so all of our overtones, okay? And we can measure this. I have that program on my computer, I can show you. So this graph, when it looks like this, it sounds like E. When it looks like this, it sounds like A. When it looks like that, it sounds like ah, etc. Okay. I can show
And
you
then
on
when
the
it
computer.
when
real
it
quick.
looks at the one on the top right there, that's just what it is right at the vocal folds,
Right.
right?
So that's if we measured it right here. So if we take this and we measure this, it's going to look very even. Okay. You like that sound, don't you? And so if we put the resonator, our vocal tract on it, which has its own pitch. If I hit it like this, it goes. That's the resonance pitch of it, right? It's like, right? And then I play it, it's going to sound different because it amplifies or de-amplifies certain overtones.
So on the y-axis of these graphs, that's decibels, right?
Yes.
Okay.
Yep. Remember, so it was decibels,
Perfect.
frequency.
Thank you.
Yeah. They call that spectral slope. That's something we'll have to talk about, okay? Do we need more clarification on this? We can go through it as many times as you want.
That was very helpful. Thank
We
you.
have lots of time for this. Yeah?
It's like that vocal spectrograph or whatever that when you sing into it like shows you.
stuff.
Is that what it is? I
Yeah.
don't know.
We're going to talk about it
Okay.
next class.
But that's what it's showing, right? Is like which ones are louder, which overtones are louder.
This is sort of. Do you want me to jump ahead and talk about that really fast?
No, it's okay. But
Okay, somebody wants me to. Okay, hang on.
The thing is,
So this is going to be really fast, okay, guys? I'm just going to show you how this works, like in real life.
Oh.
What's that?
I took that picture
Oh.
in Detroit. Oops. Okay, so this is, you guys are all going to be doing this. You can, I made these programs available. It's something that you're going to do, and that we're going to like do this together in one of the classes. Okay?
Is this the program that you said wouldn't work on math?
Yeah.
Okay.
What sounds not responding?
I think I'll stick with that.
Okay. So if we do this, this is a spectrograph. Okay. So this is taking the sound and analyzing all the overtones.
Right
Okay.
now?
Yep.
Oh.
Hey!
Bye.
Hey!
That's amazing.
So if I play a note on the piano, you'll see all the overtones go up. Okay.
Wow. Wow.
Right. And so if we play them higher, they're farther apart, right? Okay.
Wow.
So we can do this with our voices too.
Yeah.
So basically what I'm saying, if I was going at my sound source, all of those would be even, right? Kind of like that. And so if I want to change my vowel, I change where I amplify the harmonics.
Oh my gosh.
So I'm going to sing and you'll see how they do it, okay? So if I go,
This is awesome.
and so if I change, so this one's amplified here, this is at like 2000 hertz, right? And then it goes down a little bit. I don't have it like all calibrated because I wasn't thinking I was going to do this. And then, so this is E, A, Ah, looks like this. So we get amplification down here and then moves here. E, A, Ah, O, Oo. Okay?
Cool.
And so you can actually see your vibrato in there too. Can you see? Yeah.
Science rules.
What's up?
I'm just wondering what the second one from the bottom is, because that one looks like it's pretty steadily also.
This one?
Yeah, that one. What is that?
That's the fundamental I was singing. I think.
Oh, that's like the,
Yeah. So like this is like the pitch I was singing.
oh.
Okay, so now we can also do it this way. Okay, so that's what's called a spectrograph. So it goes over time, so we get the frequency we have here on the y-axis, and then on this side we get time, right? So time goes by, And then on the z-axis, coming towards us, that's what amplitude is. So how dark these lines are, right?
Yeah.
Okay. So we can also do it this way. So this one is just like instantly what's happening. Okay. So when I was talking about the this part, how it shows this is what we're looking at with this program.
Okay.
Okay, we're looking at this and how it changes instantly in the moment, right? So if I go, see how they move?
Yeah.
Wow.
Okay, and I can do it so you can really see it if I do like.
Oh my god. It's like that's amazing.
Okay, good. So we talked about that, right?
You know it.
We will talk about more about that next class, okay? We kind of have to know this information before we go and analyze all this stuff, okay? So that's how it works in real life. We only ever hear this, okay? So we have to infer what this is. We can't ever actually measure that, okay? Because we can't measure the line. All we can measure is the harmonics, because that's all that we produce, right? So when we're changing vowels, what we're trying to do is get the harmonics to go in these so that they're as resonant as possible. That's why it's a resonator, okay?
Yeah.
Yeah.
Good. Okay, so this is a little bit more about how it works, okay? This is the power spectrum of the vocal tract and the sound characteristics. So you have 4 or 5 different formants, okay? Formants are resonances of the vocal tract. That is a term you all need to memorize like the back of your hand.
Will you say that again? That sentence you just said, it was a good one.
Formants are resonances of the vocal tract. That's like inertia is a property of matter. when it comes to
Wait,
this
but I
class.
want the other one.
Okay, we'll talk about that more in a second. So basically, they're labeled like this: F1, F2, F3, F4, F5. Okay. F1 and F2 make the vowels. So what we hear is vowels. If I say E, A, A, O, U, you will hear the changes in where F1 and F2 are. Okay. That's where most people live their lives.
F1 and 2.
Yeah, F1, F2. However, we're singers, so we get this thing called the singer's formant, okay? Which is an amplitude boost up around here, 2,000, 3,000 kilohertz, or hertz, they're not kilohertz, 2 to 3 kilohertz, right? Which makes it so we can get heard over an orchestra. So if you have a lot of ring in your voice, you're singing with a lot of singer's formant. Or you're lining up your harmonics to be right with your singer's formant, okay? So I can do things like this, oops, which we will talk about more. So if I sing an E vowel that has a lot of singer's formant in it, you'll see a lot of amplitude right here, okay? So let me do that. So if I go, right around 3,000, right? So mine's lower because I'm a bass. Okay? If I sing it with really not a lot of ring in it, E, it's not the same as strong.
Wait, but it's higher.
Yeah, because I made my voice shorter too. I wasn't doing it right. Because I was going E instead of E.
Oh, okay.
Okay, yeah. Good. Okay, so it has to do with a million different factors, right? So that's why we can't talk about this yet. Yes, Michael?
What is the difference in a graph like this between like a person, say like a singer who has just like a ton of ring in their voice, but like you can't really hear like the core of their voice? How do you, I guess, scientifically define somebody's core of the voice, like the actual timbre of the instrument?
Your timbre is created by your formants and what your harmonics sound like.
So that probably means that they're amplifying one formant much more strongly than the others, so it's really shallow.
So there's this huge thing we're not going to talk about because it gets really complicated. But basically, so they talk about it in difference between Pavarotti and Domingo. Okay.
It's his birthday today.
Oh, really?
Yeah.
He's talking about
Praise.
So Pavarotti sings in his vowel formants. He tunes everything really well in the vowel formants. Okay? Domingo sings in his singer's format. That's why he sounds darker.
Oh.
Okay? So there's and tenors have a much more, it's easier for them to do it because of where their voices lie and what pitches they sing in their resonances. So it's very obvious with tenors. But so like baritones and bass, we can all do that, but it just depends. Okay?
Okay, I have a question.
Yeah.
So these formants, like, they take, like, they're concentrated at, like, specific points in your vocal tract too, like, right?
So the formants are created by the differences in the tube lengths.
Right.
that we talked about in the
single
other.
formant comes from the ventricle, and the other ones are like, that's why, like, when you talk about backspace and stuff, like, because, like, some of them are, like, behind. They do have, like, a spatial coordinate, approximately, right? Yes, that's what you were saying.
Yeah, yep. We're not gonna like really get into
Okay,
it, but
yeah, that was just what I was.
so they have a spatial coordinate. They're based on the shape of everything that's in our mouth, which is why so when our tongue moves to E, it sounds like E because it changes the form, it's because it changes the shape of the resonator, right? And an ah, it's a different shape. Make sense?
Mhm.
Good. We'll talk about that a little bit more too. Okay. Okay, so I wanted to show you guys this little thing. So there's this graph, which is, let's say these are, our vowel formants are which formants?
1, 2.
1 and 2, right? And 3 and 4, 5 is the singer's formant, okay? They say, because they're so close together, sometimes they say they're 5 and sometimes they say they're 3 of them, right? Good.
So when you say that Pavarotti, he did his, like he sang in F1 and F2,
Mm-hmm.
does that, like, does it mean that he's softer?
No,
Oh, okay. It's
it
just
means
like
that
how
he
it
didn't have
sounds.
as much singer's formant ring. So he didn't have, so singer's formant gives us ring, but it's with like the depth of our voice. That's where we hear it, okay? We don't hear it with the ping. The ping is when we hear it in the vowel formants. Because it's closer in our hearing range.
Oh wait, can you repeat that?
Yeah, can you say that once more? I just
Okay,
didn't
so if we hear like ping, like like
Yeah.
that, it's really in the vowel formants. It's really strong in the vowel formants and not in the singer's formant. If we hear like oh, it's more in the singer's formant.
So more like size of voice is more in the singer's formant and like ping and ring and.
Depends, yeah.
Which one is ideal?
It depends on your voice.
So I can think going into this step forward.
It depends on your voice. They're both ideal, right?
Well,
Okay, because I mean, so what we're talking about, we're observing, remember for this class, we're observing what happens. Okay, so we're observing singers singing with an orchestra that already do opera stuff. And then we're deducing all this stuff that happens from that. We're not saying this happens, so you have to do this when you sing on stage. Okay? So we're just talking about how it works. We're not talking about which one's better and which one's worse. Okay? But remember, there's like 3 million different combinations of resonances in your vocal tract, so you can pick 1 million of them, and it depends on what kind of dramatic intent you're trying to get across, right? Okay. And that's getting too much on pedagogy, so I kinda gotta stop talking. Okay. So then we get this thing. So in this thing, it's a link. So this slider on the bottom, right there, controls these lines. So the lines are our fundamental pitch, right, would be the first one. Yeah? And then the first harmonic is this one. That's the octave above, right? And then we get the octave in the fifth, etc. Right?
Okay.
So if you look, if we're singing down here, we get tons of harmonics that fall into all of this stuff. This doesn't change, right? But the harmonics change with what pitch, frequency we're singing, okay? So if we sing a higher frequency, there are less harmonics that go in the formants, okay? Does that make sense? I need this to make like 100% sense right now.
Oh, right now?
Yeah.
The higher the pitch, the less overtones, harmonics you find in the.
There are fewer harmonics because they're farther apart, so we can't hear them, right? Because our hearing only goes up to about 20,000 hertz, which isn't even or it's like way over here, right?
Well,
But like once you get up here, like what's an octave above 4,000 hertz?
8,000.
8,000, then what's an octave above that? 16. So there's only 2 more octaves in our hearing range up there, right?
Yeah, so based on like this overtone series, lower pitches contain a whole bunch of pitches we can hear, and then the higher ones will contain less.
Right. Yep. Which is why lower voices sound deeper
Here
and higher voices sound clearer, right?
because they literally
Yeah.
are in terms
So now there's something else to be said. So if you're a soprano and you're singing a high C,
Stop.
which is right here at 1,000, look how many harmonics you get to resonate. 2.
Interesting.
That's so weird.
Wait, what's that first line? Oh, that's the
This is the
actual
fundamental.
frequency, that's the
Okay, so
one.
don't worry about like what this actually looks like. This is the fundamental. You get to resonate 2 harmonics, and your second one is already in the singer's format.
of. So that's why they tell
That's why-
voices like that to sing like to focus on.
To not even sing a vowel.
pitch.
Right, yeah.
So, yeah,
That's why it sounds like ah, because it looks like ah looks like this.
Oh, that's cool.
Yeah.
Is that why some teachers will say, when you're supporting the high, you don't need to like work as hard as the low?
No, that has to do with something else.
Okay, never mind.
Talk to Dr. King.
Is
about
that why,
it.
is that why you
That's
can't
not much
sing,
else.
is that why
Okay.
women can't sing E up there? Because there's just not like the
'Cause-
shape?
They can sing it, but we can't hear it.
Got it.
Okay? Because it doesn't sound like E. It sounds like ah because of where the harmonics are.
Just needs a little more E.
Now, okay, so this is all about like how we hear it. This isn't about like technique. So if you want to sing a little more E, there's a whole plethora of papers you can go read about like why that works. But this is just what we hear, right? Does that make sense?
Okay.
wow. Sing. That's pretty cool. That's pretty neat.
It is. And you guys can go play with that. So that link to what I just showed you is this one right here, okay? You go check it out. We're actually doing really well. Okay, so this is another graph of what we were talking about with the spectral slope source right here. Then we get the filter, that's the formant, right? And then we get what the output, this is what we hear, okay? So this graph points out, so if we have a lower fundamental pitch right here, we get more overtones because they're closer together. They're present in the other one, but they're just really far apart, so we can't really hear it because there's kind of a cap at like 20,000 hertz, right? So then we put them through this formant, this resonator, these formants, there's 3, and then we get this shape, okay? Because we get the fall off here, and we get this shape, it makes it do like this, falling down. Yeah? Make sense? Okay, good. So then when we go and we sing a higher pitch, higher fundamental pitch, they're farther apart, because this one's at like 200 hertz. So this is only an octave above this one. We put it through the same filter function or formants, we get this output. And do you see how that could sound so much different than that? And it's only an octave up. And I mean, that's like singing a low A, and that's like singing a low A that's like at the bottom of the piano. Right? We're all savvy? Okay, formant, resonance of the vocal tract, yeah? They're labeled F1, F2, F3. That's why it gets really confusing when you talk about overtones because they're labeled 1, F0, or O, right? Remember what we talked about?
Yeah.
So when we read the chapter on registration, you guys are gonna have all kinds of questions.
Yeah.
Okay, so in acoustic literature, they're backwards. The formant actually, so when you talk about like sound, not when we're talking about singers, formants are like the physical sound and a resonance is like the actual filter of it, okay? You're not gonna get tested on that, I just want you to know that. And so if you ever read something, you're like, why are they backwards? You're like, oh, some of them talk about it being backwards. So that has to do a lot, like if you're talking about room acoustics or something like that, they refer to it that way, okay? So the formant is what we hear as the amplification, the resonance is the filter, okay? But we can use them interchangeably in this class. Formants are what amplify and enrich the sound provided by the vocal tract, by the Gladys. So when we were talking about the definition of resonance, right, there was one that was enrich and, what did I say?
Intensification.
Enrich, intensification, those are what formants do, right? Resonance, that's why they're resonance. Okay, F1 and F2 are what make vowels intelligible, you need to know that. And F3 through F5 are what is called the singer's formant. They also call it the singer's cluster. Some people think it's only the 3 and 4, it really depends upon what you're talking about, okay?
And do you always have like 3 and 4? Because on a lot of the charts, in a lot of the graphs in the chapter, it just looks like there's 3 whatever bumps in the graph.
So
Is that because 3
because
and
it's a
4
cluster?
are so close together?
Yeah.
Okay.
So it looks really close together.
Thank you.
But they're 3 and 4 because they're in our tube lengths.
Mhm.
They're that close together, right?
Right.
Let me just make sure. Yeah. They're just, that's where they're lumped together.
Okay. Thank you.
And these graphs in here are very rough. That's not like exactly what they look like. Remember that the reason we all sound different is because our graphs of those are all uniquely sounding, right? Okay. Cool. It's really hard to measure this stuff because all you see is this part of it, right? So everything else that we see is theory. I mean, like, we can kind of measure this, but it's really hard to. You have to like stick a microphone like way down somebody's throat. Okay, so this was the quarter length resonator. So we get all of these harmonics depending upon where, like, which wavelength is getting resonated, right? So if we get, this is one of the quarter, that harmonic, the first harmonic that we hear in our resonance, that's the one we hear. That's our fundamental pitch, right? Is that long. And then our third harmonic, which is the octave and a fifth, we hear is that long, okay?
Ooh, I like that.
Yeah. I just put it in there to clarify. Good. So this chart is what all the vowel formants basically look like together. They help us understand each other. It's an acoustic filter. We need 2 formants to hear what our vowels are, and the other ones are made for ring. So some people don't have a really strong singer's formant at all. So like people, amateurs that you hear in choir that try to sing and everything, they don't have a strong singer's formant because they don't know how to access it, right? In their voices. Whereas, because if you sang with your singer's formant, you'd stick out of the choir, right? Because it helps you get heard a lot. Whereas sometimes if you have a choir that all sing with singer's formant, it sounds really awesome, right? So, it kind of depends on your abilities for all that stuff. So we have this graph, the same thing, it's got frequency over here, we get 1,000, 2,000, this is where the singer's formant's gonna be, around 3,000. Remember these change depending upon how long your throat is. So this is just, that's why it's so general, right? So like Allie's voice would have a much higher, all this stuff would be much higher compared to mine. Good. So this is kind of where we see, the first formant down here for E, they're far apart. E, they get closer. A, they're as close. That's why this one's red. They're the closest ones. And then they change here, okay? Yeah.
Is the singer's formant always between 2 and 3,000, or does it change depending on what vowels you're singing?
It changes, see?
Oh, that is the singer's formant
Yeah.
that you're showing right there.
It doesn't change that much though, right?
Okay.
Compared, so we get the intelligibility of the vowels by formant 1 and 2, not by the singer's formant. But we can tune our singer's formant so that we put the overtones, harmonics, partials, whatever that we're singing in the singer's formant to make us as loud as we can be. Or as resonant, right? This is why, remember, so when we sing with the most resonance, it doesn't have as much effort with it because our vocal tracts do the work for us in amplifying our sound, right? Okay, cool. Now I'm gonna show you something that'll blow your mind after this. This is kind of what the vowels look like. And so we can like guess, this one is E, so it's strong down here, and it's weaker up here. And this is like 280 hertz, which is a really low pitch, right? So you can see how they're so confusing because it looks really hard to do. And so some of the programs that I gave you will actually like guess what you're singing for you. I don't know, it's weird. Because like the thing is, we can hear it, like no matter what, if we're singing like an E, we can hear E, we don't need a computer program to tell us if we're singing E or not, right?
Mm-hmm.
We just need to know how it works with performance.
Because we're
Good, so this is the model thing, we're gonna talk about this next time, okay?
Mm-hmm.
It's basically a program that like models this stuff, so this is the spectral slope, we can change it, these are the formants, and then it like puts it in the computer and it makes a sound for us, okay? I'll show you next time. Cause your homework, you have to use this to do some stuff, okay? Physicality of vowels, okay? So this is how this like physically happens. Vowels are created by three physical shapes. The location of your tongue, that's the biggest one. That's what we always talk about when we're talking about E, A, O, U, whatever, right? Good. The shape of our lips, that's how we get O and U, things like that, because we're changing the shape of the opening of that part of our vocal tract, right? Cool? And the opening in our jaw. Sounds different, right? Good. So these are the 6 rules for formants. I don't really want you guys to know this, I just want you to know how it works, okay? So if we have constriction in the front, we get a low first formant and a high second formant. What kind of vowel would that be? Just think about it in regards to your tongue.
Back though.
Hmm? Okay, so low and high are referring to frequency.
I have no idea.
Like the E.
Low first formant, high second formant. Which one would it be on this graph?
E.
Yep. Low first formant, high second formant. Yeah, I know, it's weird. So that's constriction in the front, anything that's like E, that's why our tongues are so far forward.
Oh. That's very exciting.
Okay? So constriction in the back would be high F1 and low F2. What do we think that would be? Whoops, I went the wrong way, y'all.
Yeah, okay.
A.
You said.
What are we looking for?
So it's high F1 and low F2, right?
Oh.
Wait, there it is.
High F1, low F2. Okay,
Okay.
let's go back.
Ah.
Yep.
What is
Ah.
that?
So now remember that the ones down here don't have to change that much. Because they're just in like your first harmonics or whatever. And then these ones change more. Okay, good. So that's the difference between E and A, right? So now vocal tract lengthened, we get a low F1 and low F2.
Ooh.
What do you think that would be?
Low F1 left.
Ooh. Because it's lengthened, right? It's longer. Ooh. You don't have to know this. We're just going through it as a class so you understand how.
Higher is shorter, gotcha.
Yep. Okay, vocal tract shortened. High F1, high F2.
E.
Ah.
Ah. Good. So when you're belting and you have to like raise up your vocal tract to sound like ah, you do that, right?
Okay,
Well,
so I have a question. Do you know
What's up?
the thing I was asking about earlier, like the spatial regions and that the formants are
Mhm.
associated with? Do you know what those are?
Not right now.
Oh.
You can find stuff that'll tell you all about it.
Oh, I was just that would help.
I know, like, you can find stuff that'll talk about it, and like, part of the thing is they can only like guess at some of this stuff, because they can't actually like measure it super, because what they would have to do is do it section, but like, they would have to take a vocal tract, cut it apart, and measure what comes out of it. Do you know what I mean? Like, and I've seen them do, like, they have videos of like pig larynxes where they like make it vibrate and things like that, and so, which is actually really cool. But I don't think they've done it with humans. Good, okay, so that was vocal tract shortened and lengthened, right? So we had ah versus ooh, right? Those are the differences in that one. Lip rounding, spreading. Low F1, low F2, that's lip rounding, which would be the same as ooh, right? And if it's spreading, e, ah, right? Increased jaw opening, high F1. So and ah are all more open jaws than the other ones on the other side, right? So, and that's where we get the arc in the middle. Do you see how there's like a million things that make this come together?
Yes.
That's what I was thinking. Okay, yeah.
A million exactly.
Good, okay, and then we'll look at, so you can actually like measure a lot of these things. The best thing that we have to be able to, feel like the closing at the bottom of the vocal source is if we can like hit our throats when we do it. I'm gonna see if I can do it, like you do like this when you're talking.
Oh, yeah.
Sometimes I can do it.
Whoa.
I'm not really good at it, but anyway, some people, you have to do it down here, Cody. Cause you have to do it at the bottom of the tube, right?
I'll do it, Alex can do everything.
Alex and
Oh, I thought that was.
Sweet, cool, so if we took this, and we're gonna do this in real life now. So this is our, vibrator. I did it nice and quiet. And then we get it in our resonator, right? And now if we change the shape of the resonator, we will get different vowels, right? So this is what it sounds like just open. And then if we did this, what vowel does it sound like? It's not gonna be super close, but. Okay, so people are saying ooh and some people are saying e. And those are like on the opposite ends of the spectrum, right? Let me try it again.
How are we supposed to?
Listen.
Oh.
Sounded like ooh.
That's right.
Okay, so where am I putting the constriction?
Oh,
No,
Low,
low. High.
low.
no.
Constriction. It's one of these two.
Back.
In the back. Which makes it what?
Ooh.
Ooh.
High F1, low F2.
I was so.
I have one.
Yeah. Good. I know, it's not like monolithic, right? And then so if I did this one,
That's ooh.
yeah.
You know.
Oh,
That was
I
ooh.
get it.
I heard it.
Cool. This one also has like a lot of E in it. Okay. It's close. And if you notice, those ones aren't like from here. It can be close. Cool. Formant regions. How simple we have. Oh, we're doing great. Okay, so the pitches that we sing don't always fall in the formants that we create with our resonance, right? If you remember, if we go back to this guy. So if I sing this pitch, I'm not resonating a lot of my overtones, right? That one is de-amplified, that one's de-amplified, right? So what can I do in order to amplify those ones? Huh?
Your tongue position, like make sure it's in a more forward position.
Keeping your larynx.
But what would I be, if I change my tongue position, what am I doing?
Well, you're not changing your
Changing the sign.
What do I, okay, so if I'm singing this pitch, I can't change the frequency, right? Okay, because I need to sing that, that is dictated by Mr. Mozart, okay? I don't get a choice. I have to sing this frequency. What can I do in order to amplify my overtones more?
Make sure it's a pure vowel. I don't know.
Close, but what's a pure vowel?
Like that. Your things look like that.
Right, yeah, okay. So what do I have to do? So I have to change what? What affects what my vowel sounds like?
Articulators.
It's the title of everything we've been talking about today.
Formant.
Formants, okay. So I have to move my formants.
Which you do by manipulating your articulators.
No,
But moving the
Oh.
harmonic closer to the formant frequencies?
no, I can't move the harmonics, they're dictated by the pitch, by frequency.
I thought that
Then
was.
then what
Chelsea
does
was
that,
almost right.
oh. What does it mean to change your formants?
What are your
I thought-
articulators? That's the wrong word.
Everything.
Well,
Your vocal tract. Change the length.
You have
and
to change
the,
your vocal tract.
There we go.
There we go.
Your articulators are your
Got the
tips,
answer.
your teeth, your tongue, and your lips. Okay, they're not like your shape and everything.
I thought that
Yeah, it's close, that's why it is. You were the most close out of everybody.
It's also a little confusing because we were talking about articulating the sound earlier with that singer's the only instrument that can articulate using the resonator, which is
Right.
a different kind of articulator than the tongue, the teeth, and the lips.
I think
Right.
Yeah, that's what I meant.
So we can change we have to change our resonator to change our formants,
Which I
right?
thought was an articulator.
Different
Sure.
category of articulation.
Yeah, it's a different, there's a
That's
lot of,
right.
this is why this class,
not about-
you have to take it like 3 times, it's because there's a million words for everything, okay? So we have to change our formants by changing our resonance, which changes our vocal tract, right? Okay, so if we moved where these formants were, we could change what the amplitude would be.
And I think he has that in here.
How do you change your resonance without changing?
How do you, what was that? How do I change what?
I don't even know what question to ask right now.
Sorry.
I think you have
So we change our formants by changing the shape of our vocal tract, right? So what we would have to do is change where these are so that they would match up more with our overtones, okay? Basically what that means is that's what vowel modification is. Okay? So some pitches don't always fall within the formants that we're singing. So if we sing E, but it's not like, because I can sing E, E, E. Those all have different positions in the formants, right? But it's the same frequency I'm singing.
That's right.
Everybody got it? Cool. But they all have different resonances, which is changing the formant, okay? So sometimes we're trying to sing a pitch where the formants don't match up with what our overtones are, and so we have to change the overtones, and that's what's called vowel migration, sorry. Because we're migrating the vowel so that it matches more with the overtones, okay? So if they're saying something like, you're singing a high ah, and somebody tells you to put more eh, or more e in it, or oo, or whatever, they're trying to get you to do vowel migration so that your formants line up with your harmonics. Okay, and then you sound more resonant. Because otherwise you sound dull, because there's parts of your harmonics that are cut off, right? So any questions about that? No, you all are experts on this. Okay, so with the high tessitura stuff, ah is really difficult for high male voices in the high part because of registration stuff, we'll talk about that. But remember when I showed you about, like with female, it looks like ah at the top because all the harmonics end up looking like ah. So if you try to sing E, we will never hear E above the staff, okay? I've got a really cool example to show you when we get to registration stuff, that'll be good. Okay, but you understand like how that works, mathematics, scientifically, yeah? Cool. Guys, we only have 3 more slides. Okay, so this is a vowel chart. We can do this, so this it has 2 formants, right? First formant frequency, F1, 0 to 1200. And actually when they discovered this is kind of where voice science like really started to start happening. Because look at when this got published.
Wow.
They just not have the technology?
They were like starting to get it,
Okay.
you know, and understand like what it meant. But so like when they published this, their knowledge of the singer's format was like, oh, we know that that happens.
But that, like, correct me if I'm wrong, but that was being like taught by voice teachers for long before they sort of like realized like
Yeah.
this is a scientific
So-
thing.
Yeah, so remember that what we're talking about in this class is an observation of what has been being taught for 300, 400
Okay,
years,
cool.
right? So we can use computers to analyze this, we can talk about what's happening, and hopefully that will give you a little bit more insight to what like a teacher's talking about.
Right.
So if they're saying, put more E in your ah vowel, they're talking about migration, you're not getting as much amplification of your harmonics, right? Okay, that's what it means,
Okay.
that's the point.
Thank you.
Good, so we get first formant here, second formant here. So if we have a low first formant and a low second formant, we get what vowel?
Ooh.
Right, and if we have a low first formant and a high second formant, we get E. Good, and so we can go across all of these like this, right? And so we'll do, when we do the voice modeling thing,
I'm just gonna straight up.
they actually do, this is really cool. So they have, basically, can you guys see this?
Yeah.
So they have this map that we can use. And what I can do, okay, so basically this like models what a voice sounds like on a computer, okay? So if I play it, it has a really annoying sound, okay? And then if I stick my cursor on this,
Wait, what is this sound we're listening to?
Just like you sounded like it.
it's like a computer modeled voice.
Oh, wow.
But this kind of stuff like.
If I weren't already impressed with the fact that the computer sounds like
Yeah.
it.
And so you can see this, we will talk more about this next time.
Wait, can
But
you
if-
move the pitch up? I wanna know what that sounds like too.
Okay, so if I, yeah, I can move the picture. But, okay, so basically, let me get rid of some of this.
What program is that?
It's called Mod. You guys are gonna use it on your own too. So the red thing, so if we have like a sum pitch, right now is where F1 is here, okay? So it's low, if I play it. Okay. All of the red things are where the harmonics are, or where the formants. So this is where like F1 is, and F2, and then singer's formant, okay? So when I play it, and then I move it around on the thing, you'll see them move. See how that works?
This is blowing my mind right now.
Okay, so if I want to do it with a higher pitch, and then we change it, we will have less definition in the vowels because we don't have as many harmonics to stick in the formants, right?
Yeah.
Wow, okay.
So this is singing,
Crazy.
wait, so this is like a high, middle C's this one. So I want to sing like this. So this is above the staff, right?
Yeah.
See how it all sounds like ah?
It all kind of sounds like alien.
But it gets stronger when I put the formants, which are the red things, in the harmonics, right? Because it amplifies the sound.
Oh.
Okay,
Yeah.
cool. We will do that next time. You guys have to do some of that for your homework. And so I hope when you do it for your homework, you'll like explore with it and not just be like, oh, I did what Mr. Besh told me to, or Chris, or whatever. All my students call me Mr. Besh. Okay. Good. Singer's formant. So it's like 2400 hertz to 3200 hertz. That's generally where it happens. Remember, it depends upon how long your vocal tract is. It's what we use to produce ring and call. So I'm using my singer's formant. If I go, hey! But if I go, hey, I'm not using my singer's formant, right? And so remember that we have a special attenuation to that in our ears. So that's why we hear it stronger too. Hey! You hear it louder because your ear also resonates that sound, okay? And I can like model it with like speakers and stuff, but it doesn't actually work in this room because these speakers are super bass heavy. So it doesn't happen. So it projects the voice without amplification. Orchestras typically only are noisy up to about like 500 hertz, which is kind of like in the middle of the staff. You'll get like solo wind instruments that'll play like up high and everything, and violins and stuff, but they don't have as much oomph as a singer's voice does. And that's why you can get heard over a 20-piece string section. You know what I mean? Make sense? Science. Okay, our ears are sensitive to those frequencies as well. It's created by the laryngopharynx, which you know is like down at the bottom. Spectral slopes we talked about. Okay, so sopranos actually like sing in that range a lot. So like your first formant is in there, so your first harmonic is in the singer's formant. So that's part of the reason why you sound like ah, right? Cool. Because your first formant and your second formant are actually below the pitch you're singing. Does that make sense? Because where your formants are is determined by how long your vocal tract is. So if your vocal tract is 13 centimeters long, I think that was on the homework, right? Oh. So we had a quarter length resonator, which was 0.12 meters long, which had a resonance of 715 hertz. Okay? So 12 meters, 0.12 meters is 12 centimeters, right? Which is probably as long as Allie's throat is. So if she's singing a high C, her resonant frequency is actually below the notes that she's singing. Okay?
Whoa.
But she still has resonant frequencies that are above that.
Thank you.
Yeah. It wasn't really a compliment. It was just science. Good. So that's what I mean. So when you sing in the singer's format. Good. So this is the nonlinear source filter theory. So it's basically talking about how resonance also affects our vibration of our vocal folds. Okay, it physically does something about bringing them back together. The sound waves help push the folds back together, so when they're resonating and they bounce back off of the closure back here, that energy helps them come together. Okay, it's part of the modeling. That it's part of 3-mass model that we'll talk about. If we don't get it right, that's where we get disruptive interference because it contrasts with when the vocal folds are trying to close each other, and that's when it shuts off, like when I was doing the thing with the didgeridoo, right? Sweet, you can, that can cause your voice to crack. So like if you sing the pitch like directly in the middle of one of the formants, there'll be so much amplification and feedback of it that it can make your voice crack. That's part of the reasons that we crack. And if you notice, a lot of our passaggio notes are where the formants are. So like if you did, well, I had you do like 0.18 meters, which is like a man's voice, right? And that's like 476 hertz, which is like a C or B, right? And that's like one of your passages that's really easy for guys to crack in that note, right? Yeah, guys,
Yeah, really easy.
Cool. That's all. It didn't add my video. Okay, we're gonna watch a video. So I tried to. Never mind. So there's this voice scientist that a lot of you guys will end up reading things about. Who made he modeled Pavarotti's voice on a computer. Okay.
I would like to introduce to you tonight my guest performer. His name is Pavarotti.
Oh my gosh, she's so cute.
Wake up now, Pavarotti. We have to sing.
So this is all computer model.
Pavarotti and I would like to sing for you the aria Nessun Dorma from Puccini's opera Turandot. I'm going to make it easy on myself. I'm going to sing the low notes. He'll sing the high notes. Take it away, maestro.
Isn't that cool?
Pepperoni looks like so nice.
Yeah. So they basically like went and measured a bunch of recordings that Pavarotti had and figured out what his voice does and all these, like what it sounds, because you can extract kind of what somebody's voice does because it sticks out so much from an orchestral texture. So you can stick like a recording in those programs that we were looking at and then see exactly what it does. And then he modeled like a computer program after it. Kind of cool.
It also makes me very uncomfortable.
Okay, you guys have any questions?
We still see you live?
Do you guys understand what formants are?
Yep.
Yes, ma'am.
Yeah. What are they? What's the one phrase?
Resonances of the vocal tract.
Yes! Okay, good.
Nailed it.
I will say that scene.
Okay, so for next week, sorry, I want you to read the chapter on analysis. There's no homework for this student, okay? But read the chapters. Can you give it to me?
So great. Wow. It's taken me a really long time to figure out. I didn't
I'll even show you.
It's just like.
Just cry.
Okay.
We'll do that every day. We'll look through your performance. Oh, okay. Just so you know, get it over the video.
Hey, I wanted to talk to you about that. So I think I'm doing that thing I talked to you about, and I recommended you for something else. Okay. So I don't know if it'll pay, but.
Great.
I just
Are you John? Yeah, for sure.
Sorry, that I was like, no, don't.
No,
I didn't want you to think that.
No, it's totally cool. I just, honestly, just, I was so afraid of.
Oh, I have to hurry. What am I doing?
Hey, bye.
Can I eat breakfast today? Can I climb this up?
Okay, love you. Night.
There's no homework for next week.
Okay. Did you listen to what I said?
I must have missed that.
No, okay, read the chapter on analysis.
Great.
That's the homework. I'll send you another email about it.
Thank you.
Yep.
I believe you.
Believe who? Who are you talking to?
Arjun. Is that what you were just showing me?
Yeah.
Believe you what?
Because I was like having a panic attack about this course pack being so expensive, and Arjune's like, Chelsea, I went and I bought the course pack. It was only $80. And I was like,
Did he ever respond to your
yes,
email?
he
What
did.
he
And
say?
he was like, I'm sorry that it's a financial burden. Like if you know you can't find any way to make it work, I have PDFs of the music that I'll send to you. And I was like, oh, you. I like believe that we need to support like contemporary art. It's like one of my fundamental things. So I never like download music without buying it. And we have to listen to those for Tuesday, right?